All right, I think the audience more or less stabilized, and we're very happy to welcome Lev again for the third installment of his mini course. And so please give your full and undivided attention to his story.
Okay, thank you very much. So now I will get closer to what I will get into what we're doing with Alexei specifically. So we, as I said, we consider two categories of instanton moduli for various groups starting from U0. And everywhere we have a special object, and we send groups into endomorphisms of that special object. So let us start with the two category of the commuting variety. So I use standard notations, I think, in geometric representation theory. So G will be GLN. Unfortunately, I don't know other groups. And B is the Borel subgroup of upper triangular matrices. Fancy G is GLN Lie algebra. Fancy B is Lie algebra of Borel. So it's upper triangular matrices again. And N is strictly upper triangular matrices and small. Then N script is the notation for the nilpotent cone, all nilpotent GLN matrices. B script is the fancy way of denoting flag variety. So we will use Springer resolution. It's an important map from cotangent bundle of the flag variety into actually dual of Lie algebra, which is the moment map for the action of GLN on the flag variety. So GLN rotates flags. It's a Hamiltonian action on cotangent bundles. So there is a moment map which plays important role called Springer resolution, if you consider it over its image, which is the nilpotent cone. And finally, I assume the presence of standard Killing form, which identifies the algebra with its dual. So the commuting variety, at least from the set theoretic point of view, is pairs of matrices, n by n, with the extra condition that the commutator is 0, and then you take the quotient by the adjoint action of the group. Just a moment. So this, what you get from the algebraic geometry point of view, apparently, is something really, really bad, not even a complete intersection. So this suggests that you should not try to study coherent sheaves over what is written, at least not in the way it's written. And maybe you can turn this into a DG scheme, stack, whatever word is used, and then you will get a proper category. So I will get to it towards the end. Now, from the symplectic geometry point of view, this variety is a Hamiltonian reduction of the cotangent bundle to Lie algebra, which seems to be a very natural thing to study. So G acts on linear algebra by conjugation. The moment map is so a point here is, sorry, just a moment. A point here would be a pair of matrices X and Y, X being the base, Y being in the cotangent fiber, and the moment map is commutator of X and Y. So setting it equal to 0 means imposing the condition that the moment is 0, and then you take the quotient by the group. So from our point of view, it means that the two category of this is the G equivariant to category of cotangent bundle to Lie algebra, and everything here looks very smooth. And again, I remind you that in defining morphisms between objects, we do not impose the moment equal to 0 condition. So the bad thing about commuting variety is that the condition X with commutator of X and Y is 0. That's what makes it bad. and we do not impose it, at least not yet. So here we use extra equivariance, not in the sense that we take quotient over it, but rather we follow the weights of actions of two C stars. So these are different people use different notations for Q and T. So here we follow Homfle and categorification of Homfle polynomial. So our Q scales base and fiber in the opposite directions by weights 2 and -2, and T scales just the fiber by weight 2. So C star Q preserves the symplectic form, obviously, and C star T scales it. And as we discussed last time, the weights of—
Isn't this opposite what you wrote?
No, I think so. Here are the X weights in my notation. This refers to X. Oh, sorry, wait a minute, the other way around. Sorry. So if you look for the weights of CQ, you will see 2 minus 2. So C star Q scales X and Y in opposite directions, so it preserves symplectic form. So let me mark this. So this refers to Q, and this refers to T. So Q scales X and Y in opposite ways, and T scales only Y. And again, it doesn't match the notations that you use, I guess, that I learned from Andrei Smirnov. We always have a mismatch there. So don't try to compare this directly to your formulas until you identify what these symmetries do. And again, from the string theory point of view, I could say what they do and then compare things. So that the weights of C star T action are in fact homological degrees. So that's what we discussed last week. So generally in the two category, you have only Z mod 2 homological grading, but you can maintain Z homological grading by assigning weight to cotangent fibers, to the coordinates on the cotangent fibers. And then, although you have complexes which are 2 periodic, you can maintain Z grading. The differential will have degree 1, and the superpotential will have degree 2 if it's linear over the coordinates of the fiber. A sibling of our category is the 2 category of the cotangent bundle to the group. Now, I mention it because written here in gold. So this one, actually, so is there a way to use a pointer? I think just a moment. Okay, never mind. Sorry. So maybe I can use this. So this sibling looks very similar, except Lie algebra is traded for the group, but this one is really a center of a 3 category, which hangs above all this construction. Don't be scared by the words 3 category. And so we're almost a center. So there's certain funny things will happen very soon, and they're explained. These funny things are explained by the fact that we're the shadow of the 3rd floor in this building. So the simplest object in these 2 categories is just the 0 section. So superpotential is 0, which is Lie algebra, the base. So the Lagrangian subvariety is just the base of T star G. and its endomorphisms are coherent sheaves over Lie algebra, G equivariant. So again, this is something very nice. And what we study from the derived algebraic geometry point of view is two categories of representations of coherent sheaves over Lie algebra, equivariant coherent sheaves over Lie algebra, considered as monoidal category. So that's what we do here. Now, in this two category, we will see special class of objects. So why these special objects? Because they're almost Chern characters of objects from the three category. So here is a special, here is what a special object in our two category looks like. It's a symplectic variety with a Hamiltonian action of GLN. So there is a moment map here. Oops, sorry. So here is a moment map. And the object that we cook out of this data is this variety together with the superpotential, which is the trace of moment map times x. X is the coordinates of the base. Well, let me remind you, we use standard notations when we have when we use T star G. So our standard notation is that G is X and T star is Y or Y tilde, something like this. So X refers to the base. So you see, this object is more canonical than the general object. In general object, Z doesn't have to be symplectic, could be any variety with the action of G. And superpotential does not have to be so canonical. All you want from the superpotential is that it is invariant with respect to the action of G. It's a function on extra variety Z cross the base variety X, which is G invariant. And here it's much more. So our main object is of this type. It's the cotangent bundle to the flag variety. That's our symplectic extra. And with the spring, so mu is the Springer map, and that's the superpotential. So let's look at it in a more explicit way. T star of flag variety is Hamiltonian reduction of T star of G by the action of Borel subgroup, which turns the cotangent space Lie algebra into nilpotent radical, because you have to impose the condition that the moment is 0. So what's left is n. And then you take the quotient by b. So G in this red box, G parametrizes the flags. So group element rotates the standard flag into non-standard position. And n parametrizes the cotangent space to that flag. And here I gave explicit action of Borel subgroup, if you want to try this at home. Now I'm using Y tilde to parameterize the as an element of n. So the Springer resolution mu, the moment map, is explicitly adjoint of Y tilde by G, and it is B invariant as it should. So the superpotential is in the red box. Here it is. It's from the linear algebra point of view, it's a very reasonable expression. Again, matrix X is from the base. Y tilde is, why do I use Y tilde? Because the adjoint of X, the moment corresponding to X, will show up. So it would be natural to call it Y. So therefore, I call the fiber of cotangent bundle to flags as Y tilde. So auxiliary coordinates, G and Y tilde, and the coordinate on the base, which is X. So what is this So this data determines a Lagrangian subvariety with something hanging over it. So what is it? So symplectic geometry. We have to impose three conditions which are in the green box. That the conjugate variable to x is partial derivative of w with respect to x. So it happens to be the moment map. So this tells you that the Y matrix in the commuting variety must be nilpotent. And then the derivatives with respect to auxiliary coordinates must be 0. So derivative with respect to G being 0 says that X and Y should commute, which is the consistency. We're in the commuting variety. That's the consequence of G invariance, actually. And the fact that partial derivative with respect to Y is 0 says that matrix X preserves the flag parameterized by G. So it says that adjoint of X by G inverse is strictly it says that the adjoint by G inverse of X is an upper triangular matrix. Its strictly lower triangular part must be 0. So this says that X preserves the flag. So what did we get? Here is the picture. The black is the commuting variety. Inside the commuting variety, we have a subset of pairs XY where Y is nilpotent. And on top of it, we have flags which are preserved by both X and Y. So this is the object. So the subvariety of where Y matrix is nilpotent is well known. It's a special important Lagrangian subvariety of commuting variety. And from this point of view, why should Y matrix be nilpotent rather than simply 0? That's because it comes straight from the fiber of cotangent bundle to flag variety. That's why this Y must be nilpotent. So in this description, this is natural. And claim, I think it's true, that if you push forward the structure sheaf, plus or minus maybe some details of this thing, the vibration, then you will get the envelope that Andre would consider for commuting variety. Okay, so now let's look at the category of endomorphisms of this object. So by our definition, we have to take 2 copies of the auxiliary variety. That's why T star B appears twice. And the base, which is Lie algebra. And the difference between superpotentials. So X mu2 minus X mu1. By definition. And this is monoidal because it's the category of endomorphisms, monoidal with respect to convolution. You have 2 copies of T star B, so if you have 2 such categories, you go from 1, 2, and 2, 3 into 1, 3. Now, this category can be simplified with the help of Knorr mostly. So first of all, just because this category looks a little too big to handle. You have 2 cotangent bundles to flag variety. First, I wrote it explicitly in our notations for T star B. So 2 groups, 2 nilpotent radicals, 1 Lie algebra, explicit superpotential. That's line number 2. Sorry. So this is line number 2, just explicit. Then let us use the group to put one of the flags into the standard position. So we kill one of the G's, essentially. We kill the first G. So now we're left with 2 barrels coming from flags, and G is gone. So the first flag is in the standard position, and the second flag is parameterized by the remaining G. we have still two nilpotent matrices and the big Lie algebra. Now look at the second term in the superpotential. Now that we set G1 to be equal to 1, Y1 is totally exposed. We have trace of X times Y1. This is bilinear, so Knorr tells us that we can get rid of Y1 and the part of X which is paired with Y1. Y1 is strictly upper triangular, so it kills the strictly low triangular part of X. That's what happens. They both disappear, so we lost the first N, and G, the last Lie algebra, turned into Borel. It keeps only the upper triangular part. So this is our final product, the category of matrix factorizations equivariant with respect to two Borels over the group nilpotent radical, Borel subalgebra, and a very simple superpotential. I think it also appeared in the paper of Arkhipov and Kanstrup, this category of matrix factorization. So this one is known, let's put it this way, or at least in one of the incarnations described above, showed there. So this superpotential is linear with respect to both X and Y. So we can use this Kazul duality discussed previously in order to get rid of either X or Y, turn it into a condition that partial derivative with respect to it is 0. So recall that when superpotential is linear with respect to something living in CM, then you can get rid of it or trade it for certain conditions imposed, generally speaking, imposed in a derived way. So first we can trade away Y, which imposes the condition that X respects, you see, X is in Borel. So right now, when we got rid of first Y, this says that X respects the standard flag, preserve the standard flag. When we get rid of the second Y, this tells us that X respects also the second flag. So what we get is Grothendieck-Steinberg, which is in the most pedestrian way, is a matrix from Lie algebra together with two flags which this matrix respects. So on top of n by n matrix, you hang two flags which this matrix respects. This is exactly what we get. X respects the standard flag, that's why it is Borel, and the non-standard flag. By the way, this 2p, which shows up here, means two periodic. So to be honest, we don't get exactly coherent sheaves. We can get two periodic complexes, but we still have Z grading. We have Z. Okay, let me sweep this under the rug for a moment. About the Z grading. Actually, maybe it's not 2p. So, okay, let me sweep this under the rug now that I've thought about this a bit more. So, eventually we will find Braid group into this category. So, trading Y away gives one of the constructions of Bezrukavnikov and Risch. So I should say here, should mention their names. I'll say Bezrukavnikov and Risch, because the categories which show up appeared in their work on categorical representations of a fine Braid group. Okay, now what if we trade away X? Then we have to impose the condition that a joint of Y is strictly upper triangular. So this is a little bit dangerous. Let me explain why. So our it's formerly y tilde. Now I lost tilde to make notation simple. So y was a nilpotent matrix. So it respected the standard flag, which was the floating flag from the y point of view. But now we require that y respects the second flag. Now, since y is already nilpotent, if you simply say that y is upper triangular, it will be automatically strictly upper triangular. But x is Borel. So x says that all lower triangular parts of a joint y must be 0, including the diagonal ones. So although saying the diagonal ones 0 is redundant, you still say it here. So you over-define the condition that y respects the second flag, actually the standard flag, which from y's point of view is non-standard. So this means that you have to consider derived Steinberg. So Steinberg in a pedestrian description is a nilpotent matrix with two flags that this matrix respects. But from the algebraic geometry point of view, you have to say how it respects, how many conditions you really impose. And here you impose too many. So therefore, it should be derived Steinberg variety, as Roma will tell you. If you don't say derived, then the representation of the Braid group won't work. And here, in this story, this condition appears very naturally. It follows from the category of matrix factorizations. As a corollary of this discussion, we established that two categories are equivalent to each other. Coherent sheaves over Grothendieck-Steinberg and coherent sheaves over Steinberg. Now, this equivalence is by no means obvious. It's a derived equivalence. So it's a funny equivalence. You would think maybe there is not much difference between a nilpotent matrix and the general matrix. You just fill the diagonal somehow, and that's how you do it. No. So it's a complicated equivalence. And again, seeing this equivalence is by no means easy. But from our point of view of starting with the category of matrix factorizations, this is easy. You just start with this one, with the last line, where it says Arkhipov construct, and get rid either of x or of y through causal duality. You have two choices, and they lead you to either Grothendieck-Steinberg or Steinberg. Now, you will see a little bit later that this equivalence is also related to Legendre transform in the original two category. So there is a little bit more. Also, let me, before we go to braids, let me mention that this category that we use in all three incarnations is almost a Drinfeld center, because Steinberg variety is a Hamiltonian reduction of the product of two cotangent bundles to flags. Suppose you take the product of two cotangent bundles and you want to reduce them by the action of G. So first of all, you will impose the condition that the total moment is 0, which means both nilpotent matrices are equal to each other. So instead of two matrices, you get one. And then you take the quotient by G. But you have to be careful in how you do it. So there is some derived stuff. That's why I say almost Drinfeld center. And the reason why we're so close in our category is because our object, as I mentioned, is almost a Chern character of an object in free category. And so there is some, what's their name? Riemann-Roch, which suggests that the category of endomorphisms of our objects is the same as a center of a certain two category, of the endomorphisms of their ancestor in the free category. So it's not a coincidence. It just tells you that there is a third floor to this building. Okay, So now let's talk about affine braid group and how it goes into this category. So here maybe I should again mention Bezrukavnikov and Rish. And Arkhipov construct also. So what is a affine braid group? Actual experts will tell you that we're talking about extended affine braid group. So in ordinary braid group, points move on a disk and you trace their world lines in time. And in a affine braid group, they move on an annulus. Here is a black annulus. And to simplify the pictures, people sometimes, instead of drawing this inner hole, they draw a pole, a thick line. Here I mark it in red, which indicates where the hole in the annulus lies. So the strands of the braid can move around this red pole. And that's what distinguishes affine braids from ordinary braids. So this affine braid group is generated by, here I forgot the pool, ordinary elementary braidings, sigma I, and elements which, let me call them Bernstein-Lustig, although I don't know if that's the proper name for them. That's, here is BL1, and then, let me put here a comma, and move BL2 closer, BLI. So I'm sorry, somehow I move those strands in the negative direction. I should have moved them in the positive direction to be consistent, I think, with my sigma I notation, but sorry. So you take I strand and move it around. Again, it depends on how you view those braids. Well, the way it's drawn here, it's a very natural move. It maintains its radius, so it moves on a circle in the annulus. It moves on a circle around everybody. So it is sufficient to take the first such element, BL1, and then together with sigma i's, it will generate all we need. If you plug in the hole in the affine braid group, so you remove the red pole, then you get something which is related to Eustace-Murphy elements. So you get something in the braid group, so you get something in the Heck algebra, which degenerates into Eustace-Murphy elements. So this is a very important part of the story. So we want to construct a homomorphism from affine braids into this funny category of matrix factorizations, which is monoidal. Now, in the form in which it's written here, this one, it's not obvious that it is monoidal. So you have to go back to its original description with the two cotangent bundles to flags to see the natural nature of the natural source of monoidal structure. So if you want to describe monoidal structure in the language of this category, you will need a few technical tricks. Okay, so in case when n is equal to 1, you have a single strand. So the category of endomorphisms, here is, what do we get? Our group is C star. Our Borel algebra is just 1-by-1 matrices, and nilpotent radical disappears, superpotential becomes 0. So we have modules over C of x, that's Borel, originating from Borel, and C star modules that originates from G. Very simple. So what it, and the braid group itself, that's Z, is generated by single Bernstein-Lustig element, which is free module over C of X with the weight 1 with respect to C star action. So it's something very simple. And the monoidal structure here, by the way, is the one you would expect. You take tensor product over C of X and tensoring C star modules in the most natural way. Now, here is explicit picture of what happens in the case when n is equal to 2. So, so I parameterized the Borel matrix, the nilpotent matrix, and the group element, which traces the flag. So G describes the flag. The A21 element tells you whether the flag is non-trivial. So if A21 is 0, then the matrix is upper triangular, so it doesn't move the standard flag. So A21 is the most important part. Let me put it in a red circle. The most important part of this matrix. If you put this into Mathematica and compute the superpotential, then you see that it factors. Well, you could have expected that it would factor from the Bezout theorem. Of course, if y small is 0, then your superpotential is 0 because y capital is 0. And if A21 is 0, this means that matrix G is non-trivial, but it's Borel. So a joint of y, that's the right here, G. So a joint of y will still be strictly upper triangular. And when you multiply it by upper triangular x, the trace will be 0. So it's very easy to explain why y and A21 factor out. And then there is a funny expression which I call x tilde, certain messy thing, 3 factors. So since your superpotential has 3 factors, there are 3 ways to split them apart and write a Koszul matrix factorization, which I remind you is free module of rank 1 into free module of rank 1 by multiplication, both ways. So A21 one way, y x tilde the other way, or, well, 3 ways to split it. I indicated them here. So the first Koszul matrix factorization, which keeps A21 apart, corresponds to the identity braid. So let me make claims. By the way, if you want to relate this to Bezrukavnikov-Risch for the Grothendieck case, then you simply set y equal to 0. It's very easy. And then you will get Koszul complexes instead of Koszul matrix factorizations, because one of these 2 differentials is always proportional to y. And if you want to get Steinberg description, you set x tilde equal to 0, but then it becomes murkier. So A21 setting it equal to 0 makes some sense. Why should it be identity? Because A21 tells you how your second flag is different from the first flag. Then the matrix factorization in which x tilde is killed. I'm sorry, let me make a comment. As you recall, matrix factorizations live on critical locus. So product of A21 and x tilde is in a sense more or less equal to 0 up to homotopy. So when you say A21 equals to 0, when you make A21 part of the differential, you say more than A21 times x tilde is 0. You kill A21 specifically. So that's identity. And if you kill x tilde specifically, making it one of the differentials, this corresponds to both positive and negative elementary braids. The distinction between them is the weights with respect to 2 Borel groups, subgroups, which recall that our category of matrix factorizations is equivariant with respect to B cross B. So the distinction between positive braid and negative braid is just the weights of Borel cross Borel. Very funny. And if you make your third choice of splitting, then what you get is the Kazhdan-Lustig object. So if you're familiar with how Kazhdan and Lustig categorified affine Hecke algebra, or whoever did that, maybe it wasn't Kazhdan and Lustig, I'm sorry. Apparently Alexei is not here, or he would have corrected me. So they had some funny objects which gave exotic T structure, and these objects are related to so-called perverse sheaves, all that story. So here they show as the third choice of splitting three factors in the superpotential into Koszul matrix factorization. So maybe we'll mention those objects later. Now, if you split, so if you have a superpotential which is three factors, and you consider three corresponding Koszul matrix factorizations, then you can check that they form exact triangles in two ways. These form two exact triangles. I don't write it explicitly. Oh, sorry. So they form two exact triangles. As people, so in categorification of link invariants, starting from Mikhail Kavanov's work, this is how elementary braid crossings were categorified. So first one would come up with identity braid and with Kazhdan-Lustig object, and then take their complex to take their cone one way or the other to represent braid crossings. So here we see the same pattern. The Bernstein-Lustig elements, the Eustace-Murphy or whatever you call them, are simply the shifts of Borel weights. So they're represented by Koszul matrix factorization of the identity matrix, but with funny Borel weights. So those are easy. As you know, they form a commutative subgroup in affine braid group, and their categorification is supposed to be easy. Well, actually, if you use categorification by Zergel by modules, which is quite popular, done by Rouquier. Rouquier did for ordinary braid groups, I think. Then these Bernstein-Lustig elements will be represented by very complicated complexes, and so it would be by no means obvious why they're commutative. Well, maybe I'll say it again when we get to ordinary braids. Okay, what's the algebraic explanation of these formulas? So this is how Alexei explained it to me. So I'm repeating his story. And this comes from Risch and Bezrukamnikov, I guess. So suppose that matrix, so the explanation on the Grothendieck-Steinberg side seems to be rather natural. So there your matrix, so you take your matrix X, assume that it is simple and regular, which means that X11 and X22 are not equal to each other. Let me remind you that X is upper triangular and these are diagonal elements, so they're also eigenvalues. So then such matrix X in general, upper triangular X, would preserve n factorial flags, and each flag orders eigenvalues of X. So the set of flags is the same as the set of orders on n elements, so the permutation group acts on this set, changes the order. So to a short positive braid, we associate a condition that the second flag respected by matrix X is a permutation of that braid applied to the first flag. So again, I remind you that in Grothendieck-Steinberg variety, we had a triple matrix X from the algebra and two flags which it respects. So now you say, in that whole variety, let's pick subvariety where flag 2 is sigma applied to flag 1, meaning the ordering of eigenvalues coming from flag 2 is the ordering coming from flag 1 and then permuted by sigma. So in our case, n equal to 2, these two conditions exactly correspond to A21 being equal to 0, which says that both flags are the same, so permutation is identity. Here, it's this case. Permutation is identity. Or if you say x tilde is equal to 0, that's a long factor in W. This says that the eigenvalues are permuted. So again, with the help of Mathematica, if you conjugate your matrix X, and you will see that the eigenvalues are permuted. You impose the condition that the lower left entry is 0, the eigenvalues are permuted. So that's why we get the first two choices for our Kazul matrix factorizations. They say that permutation is either identity or switches the eigenvalues of X. The Bernstein-Lustig elements are always shifts of Borel weights. So this tells you why the inverse of 1, 2 should be similar to the 1, 2 braid itself. Consider the second Bernstein-Lustig element. The second strand goes around. You see from the picture that it is a composition of sigma 1, 2 inverse, then first Bernstein-Lustig, and then sigma 1, 2 inverse again. So from there, you see that sigma 1, 2 inverse can be expressed in terms of sigma 1, 2 and two Bernstein-Lustigs, which simply shift the weights. So if you found your matrix factorization for positive braid in the realm of a fine braid group, you also know the inverse one from this formula. This is convenient. So that was algebraic geometer comment. Now here is an emotional physicist comment. Where is the braid in this story? Now, where are the strands? Where are the ropes? And naively, you would think that the eigenvalues of X are braided. At least that's what the previous story suggests, that you're trying to permute eigenvalues. Except that the most interesting from the algebraic geometry point of view, the juiciest part of this category is where the eigenvalues are the same. Which of course contradicts your suggestion. So the correct answer coming from, partly at least, from physics is that well, in string theory, you will see the braids, you will see the objects that move, you will see those ropes. So at least mathematically, what is braided is complexified Kähler moduli of T star B. Oh, sorry, I shouldn't say T star B, I should say B. So there is flag variety. It has Kähler moduli, which do not enter the story. So these are real numbers, pairwise not equal to each other, depending on how you define them. Then you complexify them. So then instead of being positive distinct numbers, they start living in complex plane in punctured complex plane. and they are being braided in this story. But their braiding is hidden from view in this construction. And there is a reason. Again, if you go into strings, then you will see why you cannot see them move, especially the angular movement. It's hidden very well.
But Lev, would you expect a situation when the sorry, something wrong with the mic.
Yeah, I'm sorry. Could you say it again, please?
So, wouldn't you expect to have?
Andre, I think I lost.
That's my question.
I'm sorry, I think I lost you, and your mic is being switched off all the time. Could you permanently turn it on? I'm sorry, I couldn't hear what you asked. Could you say it again, please? Andre? Oops, there is a, okay, just a moment. Got a comment. What? Andre, can you hear me? Andre? Can anybody?
My mic's not working so well. Yeah, you please continue.
Oh, okay. So now let's look at the Legendre transform in case of commuting variety. So it's a cotangent bundle to Lie algebra. So we can switch Lie algebra with the cotangent fiber and recall what it looked. Well, it's a standard Legendre transform. So what do? We had an object T star B with the superpotential X mu. So now we have to add old base, old G becomes part of auxiliary variety. So now it becomes the first part of the first piece in the object. And we take the old superpotential and add to it a bilinear form, which pairs the old coordinate x tilde and the new coordinate x. So this is Legendre transform. And what do we get out of it? Let's write it out explicitly. T star B, so it's G cross N. There is Borel lurking, equivariance lurking in the background. And I wrote the superpotential explicitly here. Here it is. Explicit superpotential. Now, let me do a change of variables. So instead of the variable x tilde, which becomes auxiliary, so I can safely change it, I introduce variable y prime, which is the conjugation of x tilde by J inverse. So now my superpotential, just a moment, the first term in the superpotential, the first term, becomes bilinear. That was the point of doing this transformation. X tilde and add G turned into y prime. Therefore, and the second one is modified a little bit. You just have to substitute standard thing. So now you can apply Knorr to the first term, y prime y. They both disappear. I'm sorry, no, they don't disappear. Y disappears. Y prime was a general matrix. It was x tilde formally conjugated. So from y prime, you lose the lower triangular part, the strictly lower triangular part. So y, let me say, by Knorr. Oops, sorry, just a moment. Oh, let me say it very explicitly. Knorr Y removes strictly lower triangular part of Y prime. That's what happens. So Y prime becomes Borel. So now you have group, so N disappeared and G became Borel. So you have group cross Borel and whatever remains of superpotential. So what you get is another object, which is very similar to our original object, but it's less canonical. So you see here, you lost the symplectic story. I suspect that G tilde is, G tilde is the Grothendieck resolution. It's the bundle over flag variety whose fibers are all matrices respecting the flag. So the fibers are Borel subalgebras. Borel subalgebra is fibered over flag variety. That's what G tilde is. I suspect that it is Poisson, and this mu, which sends fiber matrix just to its representative in the algebra, that it is again the moment map. But at least it's not symplectic. So on our floor, there is a little bit more than on the third floor. So this is not the object that comes straight from the third floor without any tweaking as the original one. The T star B came from the third floor in a very canonical way. The G, which was N tilde. G tilde is a bit different in that respect. So that's the object that we got. If we played with this object, so you see, the point is that you can trade nilpotent for Borel. Now you can perform all the calculations that we did with T star B. And you will get, again, category of endomorphisms of this object, which would be similar, which would be equivalent to the category, to the first three categories that we got up there. So in fact, we'll get, sorry, well, maybe I should have said it explicitly. I'm sorry. Before I say other stuff, just a moment. Should have said that explicitly. So let's call this object, let's give it a name. Let's call this FL prime. So the endomorphism category of FL prime is matrix factorizations. That's the starting point, G equivariant, G tilde cross G tilde cross G, and the superpotential, which is exactly the same. Trace of x mu2 minus mu1. And now I will do with G tilde the same thing that I did with cotangent bundle, to flags. Namely, I will present it as group cross Borel. There I had group cross nilpotent, and now it will be group cross Borel. So I have two Borels here, and here I have group cross Borel, another group cross Borel, the algebra, and so trace x of adjoint G2 of Y2 minus adjoint G1 of Y1. So everything is absolutely similar to what we had in the case of T star B. So this is the story of N tilde, which is T star B by definition, versus G tilde, which is also a bundle over flags, but the fibers are Borel rather than nilpotent. So you get everything the same, except that you get Borel subalgebras instead of nilpotent subalgebras. So now you can put one flag into the standard position. So you lose G and G equivariance. And you have Borel cross Borel. And so here you have remaining Borel cross G cross second Borel cross G. And now you have trace adjoint G2 becomes simply G minus Y1 times X. So you see that now Y1 is Borel. So by Knorrer, it kills all the low triangular part of X in the term Y1X. Sorry, my computer starts slowing down somehow. So here we apply Knorrer. And you're left with the same thing that we had in the beginning. We lost the first factor of B, so now it's G cross B. But now our Lie algebra becomes not Borel, but nilpotent. So everything is the same, but nilpotent and Borel switched. X is now nilpotent and Y is Borel. So they switched. So Legendre switches Borel and nilpotent. Here I make a comment for future that if you continue this story, then eventually it will switch GLMN superalgebra into GLNM superalgebra. So somehow I will, so this is a beginning of a work in progress. This Legendre has to do something with superalgebras emerging in this story. Not the GLN that we're talking about, but the category 5 GLN, which is hasn't showed up yet. Okay. So to finish, let me say I wanted to talk about Chern character in this story. So maybe if it's okay, I'll just begin this. I didn't prepare the following notes very well, so there may be some errors. So what would be a Drinfeld center of our category, B2 star G? So let us define Drinfeld center as the category of endomorphisms of identity functor. Different people give different definitions, but this one is the easiest from the technical point of view, because our identity functor, as we discussed previously, is an object in the product of two categories. So I take T star G cross T star G, I switch the sign of symplectic form in one of them, that's the bar, and take the two category. So this two category is monoidal for obvious reasons, and we just need an object which is identity for this monoidal structure. So from previous experience, we know that we need Lie algebra so that its element will impose condition x1 equals x2. So you have x1 here and x2 there. And you have to somehow equate them. So that's how we did it think, a week ago in case of one-dimensional spaces. But also we have two equivariances, first G and second G. So you have to reduce equivariance with respect to G squared. Well, you have to make them equal in your object. So the proper way to do it is to introduce another auxiliary variety, which is the group, on which G1 and G2 act by left and right multiplication, or right and left multiplication. So that would equate the action of G1 and G2. The difference between their actions could be used to rotate the element of G into identity. So therefore, the identity element becomes the special one that we discussed in the beginning, only in the case when you have two Lie algebras, two copies instead of one. So it's a cotangent bundle of the group. And the superpotential is, if I wrote it correctly, is the right moment times x2 minus left moment times x1 of the left and right actions of the group on itself. So if you write it explicitly, cotangent bundle is it's trivial, so it's G cross Lie algebra. And left and right, these moments maps are left invariant and right invariant vector field. I hope I didn't mix them up. So here they're written, gy and yg. You multiply them by x1 and x2. I couldn't do it properly in my head, guys. So if somewhere I put g instead of g inverse, I apologize, and I'm really embarrassed. So then you have to do a little bit of calculation with Knorr. It's a straightforward calculation. I dropped the details, but I remember the answer. The endomorphism of identity functor will be G equivariant matrix factorizations on the space that you can describe in two ways. So you could describe it as Lie algebra cross cotangent bundle to the group. So where does the group show up? The group comes from, when you compute endomorphisms of the object identity, so you have two copies of this object, home from one copy to the other copy. So you have two groups G, but one of them is removed by equivariance. You have equivariance with respect to initial group G and final group G. So by acting with them, you can rotate the first group element into the identity, and then what will remain of equivariance is one group G, which will act by conjugation of on the second auxiliary group. But the second auxiliary group remains, and here you see it. So this remaining G is the auxiliary group from one of copies of identity. And by Knorr, you can kill one of two x's, and you can kill one of auxiliary Lie algebras. So what is left is one of the two Lie algebras from where x1 and x2 come, and one auxiliary Lie algebra. So now, how do you combine all these three factors, two Lie algebras and one group? You can combine them into Lie algebra cross cotangent bundle to the group and have that superpotential that I wrote there, this one. Or you can change the variable from y tilde to y. So y would be y tilde times g, as you can see. I wrote it somewhere. Y equals y tilde g. And then it looks like you have cotangent bundle to Lie algebra across the group. So either way, again, the fact that you can describe it in two different ways comes from the fact that there is a three category hanging over all this thing. Now, if you were trying to address commuting variety naively, then you would think that you, well, not so naively. What do you want? You take cotangent bundle to the algebra, which is the algebra cross itself. Here it is. The algebra cross itself. And then you want to impose the commutator being 0, so maybe you want to do it in a derived way. You know that the commutator, that the entries of the commutator are not, do not form regular sequence, so better do it in a derived way. So you introduce, an oddly algebra, an odd one, and write a Kazul complex. G, or G minus 1. And you put here a differential, which is matrix theta. So theta is from here. I should say trace. Of, to be honest, differential with respect to theta, derivative with respect to theta, times commutator of x and y. That's what we discussed previously. Imposing something in a derived way through Kazul complex, turn it into a DG algebra. But if you look at the formulas above, you see that where does this green thing come from? It's trying to do Kazul on G. This may come from doing Kazul on G, but G is not Cn. G enters non, well, in the upper version it enters linearly, but it's not Cn. So it's not clear to me that you can do this, that this would be the proper answer. That you can get rid of a group element by trading it for an odd matrix. You can surely do it for X or Y. But then what you will get is a derived reduction of cotangent bundle to the group, not to the Lie algebra. So therefore, I'm not sure what is, and again, I don't know what is the state of the art. I don't know what is what people think about the Drinfeld center of two categories associated to commuting variety. So on our side, it's a nice category of matrix factorizations that I wrote above. And I have doubts whether a derived way of imposing, that commutator is 0, whether this gives you a correct answer. So we work with this. Let me put it in with this description. So this is for us is the proper description of coherent sheaves over commuting variety. It's one of the two ways of writing category of matrix factorizations. So why did I mention it? Because maybe next time I want to begin by describing Chern functor. Oops. It will go from the category of endomorphisms of our object, that's where braids live, to this category of matrix factorizations, to the Drinfeld center. With the property that if you have an object here, then here I'm cheating a little bit, then home from this object, from identity braid or identity object in the endomorphism category to O, will be the same as home from a certain identity, what should I say? It's a different one. It's in the center. It's in the center, and everything here is computed in the center with the Chern character of the object O. So this is some form of Riemann rock. So this part I'd like to explain at least. How do you say? At least intuitively, first thing next time. So if not for matrix factorizations, this would be almost a structure sheaf. It would be a structure sheaf if we were talking about Hilbert scheme. Okay, and I think I'll stop here.
Well, questions? I apologize for earlier feedback issues, but I think they fixed them now. So it's, well, maybe I'll start with asking the question I tried to ask before. So that was where is the braid question? So if it comes from some special locus and complexified moduli, you think in general, so be some general situation when instead of your curly B have some other variety, you'll be just I mean, the fact that this is a braid, it's an accident. It's just like a pi1 of complement to some discriminant. Is it? There's some in some complex module there's some bad set, and you're just looking at pi1 of its complement. That it happens to be a braid, but it's.
Let me think. Let me think. What would be a proper way? Let me try. So why does it happen to be a braid? Imagine the following picture.
Mm-hmm. No, I understand why it happens to be the braid here, but in general, you can imagine a story where instead of curly B, you have some different, you know, something else plays the role of B.
I see.
And
curly B is a very canonical thing. So, so what are the? Maybe I should have said that instead of Greenfield Center horrors. So analogs of curly B, you can take partial, so a general object that is a general object. So take a partial flag variety, let me call it FL, partial flag variety. And take a bundle over it. How should I call it? So tilde will not be the right name, but let me call it provisionally FL, whose fibers are matrices in which so matrices of some sort.
mm-hmm.
And the condition will be the following. So you will decide in each transition between partial flag spaces. So you have Fi sitting inside, sorry, my pen fails me. Fi sitting inside Fi plus 1 and I indexes their number, not the dimension necessarily. And then each time you decide what you want. Do you want that your matrix of fi plus 1 is inside fi plus 1? That's one version for each I. Or that it is nilpotent, so it sits inside fi. So you decide between these two choices for each I. So it's a mixture between the parabolic and nilpotent.
Okay.
You decide. And so, and this would be a general object.
But you can imagine there's probably many more somehow. There are many other stories that should be kind of like what the story you're telling here, no?
So again, on general grounds, you might think that you get any variety Z with G action and any superpotential on Z cross Lie algebra, which is invariant again with respect to the algebra, with respect to group action. But it seems that these are most important ones. And
I agree with that, yeah. But
so I don't. So in string story, there is following picture. May I try to?
No, but in general, so there was this general story with like your category with Kapustin, and somehow trying to you've been telling us about this category associated to algebraic symplectic varieties and so on. There's some sort of broad generality there, and I think all I was trying to say, I think that in general the Braid group should be probably replaced by like fundamental group of the complement to some discriminant in general. So it will not have representation by ropes and crossings, and it's just something.
Do you have other examples where you have a variety with group action and some nice super potential? I just don't know. Maybe I should think. Okay, let me put a question mark.
Yeah. Well, okay. We can table this question for later. The other question I had was, sorry, my memory is very bad. Oh yeah, right. So this you assigned. So we had this. You explained the assignment for 1 braid and 2 braids. But even with 2 braids, it's satisfied when then we get to 3 braids and so forth. To say that something forms a representation of a braid group, one needs to check some relations. Are these relations obvious here, or or it's a proof, or
no? It's a so first of all, how do you get general braid out of this? So we have a canonical function from endomorphism of object n. So n means size cross endomorphism of object m into endomorphism of, again, I think it's known at the level of, I think Bezrukavnikov will not be surprised, which corresponds to putting 1 braid inside of the other. So if you have 1 braid, something blah, 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 and then you take the annulus on which it lives. So you have a bigger annulus, so you have an annulus of, so here is one annulus, and here is some other annulus. And so you can insert 1 braid inside the other braid. And this corresponds to combining, in fact, we can combine two categories of GLN and GLM into GLM plus N, I think. But okay, I haven't thought about this carefully. So let me say, oh, sorry, actually we can, yes, and I can tell you how to do it. Yes, that's, sorry, yes, of course. So it's a separate, okay, so there is a nice object which tells you, and it has a mathematical name. which tells you how to go from T star GLN cross T star GLM into T star GLM plus N. It's a, there is a name for it. It's a Grossmanian, so that's what you would expect. Take a Grossmanian in Cm plus N and equip the subspace and the quotient space with a basis.
Okay.
And take a tangent bundle to it.
Mm-hmm.
It would be something intertwining all these three. It's called, I think Cherkis told me that it has the name Stiefel-Whitney or something. So it's a Hamiltonian reduction of T star G by a very small, so take T star of GLM plus N and do its Hamiltonian reduction by the matrices which have something non-trivial here, ones on the diagonal and zeros everywhere else. I think this is the answer. So this thing will have triple action of GLM, GLN, and GLM plus N, which will be Hamiltonian. So this has, so this is Alexei, and I have to write this down at some point. Oh, sorry.
Alexei is suggesting some other names. You know, that's some name. Yeah, exactly. Kashi Schwarz-Benikovsky variety.
Sorry. Sorry. So there is this variety which is which gives you a Lagrangian correspondent. So this is a triple vertex for Nakajima varieties, if you may say it this way, or star type. Again, depending on your view. I can talk about it later in more detail. So this thing allows you to put one affine braid inside the other. Also allows you to put an ordinary braid inside an affine braid. So if you define Bernstein-Lustig on one strand and crossing of two strands for affine braid with two strands, then everything else should follow. And then you spill blood, and that's what we did with Alexei. Actually, since our category is more or less equivalent to, so there was a lot of blood spilled in trying to prove the braid relation. Maybe it should not have been spilled. Maybe we should.
So for you, it's work, in other words. In other words, for you to prove the braid relation, some work.
Yes, so yes, it is work. It's not obvious. You have to check, but it works. And it's not surprising. It is essentially, it's similar to, again, I don't want to diminish hard work that Alexei did in large part. It's parallel to what Bezrukavnikov and Rish did using the language of line bundles, and we use the language of Braille covariance. So yes, but the important point is that it is not obvious by any means. There's certain.
And how about these commutations with the? It also has to property like, you know, like the first Bernstein-Lustig generator commutes with like 2 and 3 or something like that. You know, how about proving stuff like that? That's obvious, or is that?
Yes. So that's how you get the formula for the inverse braid. In fact, you get it through this relation, that the inverse braid is elementary braid with twisted, with changed weights of Borel. So all these relations have to be checked, and since physics hides the braids, it's that's why braid relations become highly non-obvious, as opposed to other categorification constructions related to on the A side, where you have Lagrangian started by Zeidel and Smith, for example, and their braid relations are absolutely obvious. But But then they have to struggle with Q degree, for example. And in our case, Q degree is obvious. It comes from C star action. So in string language, you can see why in some models Q action is obvious and braids are hidden, and in other models it's the other way around. It's all in the spirit of your paper with Nikita on 11-dimensional theory.
Oh, okay. I don't know.
Somewhat. So it's in the 11. You see, in order to compute things, if you're not Nikita, then you go from 11 to 10 by you need a U1 group acting on your 11-dimensional manifold, and then you take the quotient by its action. And so depending on how you choose your U1, you either it's U1 related to Q degree, and when you take the quotient, Q degree disappears. It's not obvious. You could see that it was rotating something. Now you took the quotient, so you don't see this rotation anymore. It's hidden. But then the braid remains intact. Or you take a quotient over the group that does rotation around the braid. So the braid strands lose angular coordinate. Because your U1 acts in that way. The braid doesn't have to be invariant when you do this compactification. It doesn't have to be invariant with respect to this rotation. So you lose angular coordinate of braid strand. So that's part of the reason why braid action becomes non-obvious, but you maintain U1 action, which gives you Q degree. That because you didn't compactify. So you can see it here that you do rotate.
Right.
Yes, so it's a very mechanical. Everything becomes very mechanical. That's the advantage of string picture. So you have to do one or the other, or else you have to do computations 11-dimensionally, which I don't know how to do. So you have to lose something.
All right. So how about the question from the audience?
Your Gromov-Witten equals sorry, what's his name?
Donaldson Thomas.
Donaldson Thomas. Yes. Sorry, I forget obvious names. Is also as far as if I understand it, it's also a question of which U1 you choose to go down from 11 to 10. I don't know if.
Suppose.
So they all go around the choice of U1.
Okay, last call for questions from the audience. If not, we thank Lev for his wonderful work explaining such complicated theory to us, and we look forward to the next installment of that to happen in 1 week. So thank you, everybody.
Okay,
we'll see you next week. Yeah.